Okay, let's check out a couple more differential equations. These are called a first order homogeneous differential equation, um, or we often just say they're homogeneous. So what does that mean? That means we could write the derivative dy dx, right, y prime, as a function of y over x. Well, neither of these look like that immediately, and again, some clever substitution. So the first thing is to check, can you get it in that form? If so, then you make another substitution. We let v equal y over x, which I kind of wrote to the right in blue. And that leads us to a few things. First, we can solve for y, right? Y equals vx. Also, though, at that point, we could take the derivative of both sides with respect to x, and by product rule, we know dy dx would be v plus x dv dx, right? Why? Because remember f times g. So the derivative, right, f prime g, the derivative of v with respect to x is dv dx, here's f prime, times x times g, plus fg prime. So leave your v, here's f, and what's the derivative of x? It's just 1, right, fg prime. So product rule. The resultant right-hand side right here is because of product rule. Okay, so I have two examples. Let's first check, like, is it homogeneous? So we need to get y prime by itself, divide everything by 2xy. So then we're left with y prime, or dy dx, right? Y prime equals x over 2y after you reduce. So we get x over 2y plus we get y over x. Y over x. At first, it's like, this is not f of y over x. I do have a y over x, but I also have x over 2y. So how does that work? Well, one more thing, and this comes up often enough, I probably should have just wrote it, is if v equals y over x, we could also say x over y is the reciprocal, right, 1 over v, or v to the negative 1. That is also true, right? If this is true, if we do reciprocal both sides, then this is true. Of course, at each step you kind of have to think about the domain and our singular solutions, right? What if x or y or both are 0? So always keep those in mind as you go. All right, so let's go ahead and change y prime. That we can say is dy dx, okay, equals, so we have this 1/2, right? 1/2 x over y is v to the negative 1 power. And then plus y over x, that is simply v, right? This is v. Here we had x over y, so that was v to the negative 1 and the 1/2. Sometimes it will be appropriate to leave it v to the negative 1. Also, though, keep in mind, this is equivalent to just 1 over 2v. So in this particular one, we're actually going to want that because how do you proceed from here, right? If I just multiply, if I move the dx and then divide the 1/2 v, the negative 1 plus v, that's kind of ugly. So let's clean it up. We need an LCD, 1 over 2v plus the v. I need to multiply by 2v, right? 2v over 2v. So multiply 2v over 2v to get an LCD. And that would be 2v squared plus 1 all over 2v equals, so I also need to substitute, probably should have did that at the step above, but that's okay. dy dx, right? I want x and dv. I don't want dy dx anymore. So that last bit of information here, dy dx, I could substitute with v plus x dv dx. So I'm looking at this now, actually. Perhaps I could have saved a step. Okay, perhaps this was not needed, actually. That's okay. Rather than editing, I'm human. I make mistakes. Let's just think about that. If I had on the left, I'm making that substitution, v plus x dv over dx, right? Then, when I subtract v on both sides, they cancel. So this is actually really good. Let's go ahead and, I'm going to rewrite that 1 over 2v plus the v. But notice, right, when I subtract v, those cancel. I don't know how I didn't catch that, but that's okay. So we have x dv dx equals 1 over 2v, and separate the variables, right? So we move that 2v to the left and do the reciprocal of x over dx. So if dx over x equals 2v dv, oh, I like that a lot better. Integrate both sides, right? We separate our variables, perfect. Integrate both sides. And 2v squared over 2, so we just get v squared equals dx over x is ln x. And don't forget your constant, right? So plus c. And remember, our original problem had x's and y's. We're trying to find, I didn't even find the general solution, but my bad. If no initial conditions or any conditions are given to find a particular solution, it's usually implied you're finding the general solution, which just means we don't know the constant. But the original problem had x and y, so I do need to go back and make that substitution. V is y over x, right? This is y over x squared equals ln x plus c, and multiply both sides by x squared, and I'd probably just leave it at that. It's not going to get much cleaner. Y squared equals multiplied by x squared times the ln x plus c. All right, perfect. Again, that absolute value, we oftentimes in differential equations ignore it. A lot of times it's because x is restricted to positive. In the application, when it makes sense to make negative. I'm going to leave well enough alone for this problem. We might have been able to go through and justify that it is simply positive, and if you check the solution online, it probably would omit that absolute value as well. Okay. Let's do one more example here. So again, first step. Can we write this as a function of y over x? So always check, divide by that coefficient of y prime. So I'm going to divide everything here, xy, xy, xy. Oops, got a little sloppy there. And therefore, we have y prime equals x over y, and plus 3y over x. So We have y over x and we have an x over y. Same trick as the last problem. Okay, so we're going to make that substitution where we're allowing v to be y over x. So therefore this is 1 over v or v to the negative 1, either way, plus 3v equals dy dx. Okay, but then make that substitution dy dx is v plus x dv dx. Right? This is v plus x dv dx. Again, that's part of the formula, but it could easily verify why that is true. Okay, the right-hand side did not change. And subtract that v over. And in this one, I'm not seeing a way to avoid getting the LCD. So the last one we got lucky, those v's canceled. But in this one, it looks like no matter what we try, we will need a common denominator on the right. All right, so subtract the v. X dv dx equals 1 over v plus 2v. So therefore I need to multiply by v over v. Okay, and now we have 1 plus 2v squared over v equals x dv dx. Alrighty, looks good. And multiplied by the reciprocal, really everything but the dv is moving. Right, that to the right, reciprocal here. So to save a second, I'm just going to write that out, v over 1 plus 2v squared dv, okay, equals dx over x. Running a little bit out of room here. So this actually looks really good. They're both in a form of ln, right? And because if u is 1 plus 2v squared, du for the left is 4v dv. So all I'm really missing is that 4. We can multiply 4, divide 4, or to avoid a fraction, it might be even easier to just, all right, I need a 4 here. We'll go to multiply this side by 4, right? Why not? And now we are ready to integrate. So let's integral both sides. On the left, we have du over u. So that is ln u. To save a line, I'm just going to say, like, all right, I could see that u substitution, right? So that's ln of u, which is 1 plus 2v squared. And on the right-hand side, we have 4 ln x plus c. I like the plus c on that side. Okay. I'm going to show this little trick. It really doesn't matter. I'll explain it both ways, but this is kind of a neat little shortcut. This is some constant c, right? I have no idea what it is. But if I said ln c, it's still some constant c, right? Natural log c is, it's going to give me some constant. I don't know. Don't care what that constant is. Well, why would you do that? Because since this is just a random constant, and now I have ln, I could use properties of ln where, remember, the coefficient can become x to the fourth, and then plus becomes multiply. So this can become ln of x to the fourth times c. Like, why would you want to do that? It's because if you look at the Left-hand side. Oh, by the way, let's get rid of the absolute value here now because this is always positive, right? 1 plus 2b squared. So 1 plus 2b squared. And now, eliminating ln, we can e both sides. So why wouldn't it work if I didn't have that ln? So we still result in the same thing. Okay, I just wanted to throw this out there in case you ever see this. It's like, well, why did they get that? It's just because it's constant, it doesn't matter. But if I in fact had e to the 4ln x plus c, okay, now we have to think of this as e to the ln. Now I could still do this, but remember plus an exponent is the same as multiplying here, right? And now I could cancel this e and ln, and we get x to the fourth times e to the c. But again, this is some, e to the c is some constant. Here I chose ln c, here I have e to the c. No matter what you do, it's some new constant times x to the fourth. Okay, it results in the same way. It's just often people try to cancel that e and just have x to the fourth plus c, but that's not true. It's x to the fourth times c. Okay? All right. Sorry for that side note. I think it's a pretty cool trick, worth mentioning briefly. All right, so last thing, again, we don't have v, right? We have y's and x's. So 1 plus 2b squared is equivalent to 1 plus 2, v was y over x, squared equals x to the fourth times c, or actually often we'll usually write cx to the fourth. Okay. Not a whole lot we could do. Most solutions would like clear that fraction. I agree with that. It looks cleaner. Multiply everything by x squared, right? We're timesing everything by x squared. So we have now x squared. We'd clear that fraction there because we'd have y squared over x squared, so just 2y squared equals cx to the 6. And that is our general solution to that differential equation, which was homogeneous.